So in this video, I want to talk about benzene chemistry. So let's say we have this benzene compound with this X functional group. Something important to realize is we can add this second Y functional group. We could add this Y functional group to this benzene compound in one of three unique locations. For example, we could add this Y compound on this particular carbon. And if we add it on this particular carbon, we would form this ortho product. Because this carbon is in the ortho position relative to this X compound. However, we could also add this Y compound on this particular carbon. And if we added it on this particular carbon, we would form this meta product. And this carbon is the meta position relative to the original functional group. We could also add this Y compound on this bottom carbon. And if we add it on this bottom carbon, we would form this para product, where this carbon is in the para position relative to this X functional group. And again, I like to personally remember this because this is the meta position to this X functional group because this forms an M. When we add it in the meta position, we form something that resembles an M. So that's how I remember meta. And again, this is the para position because these are parallel. So that's straightforward. So that's how I remember the para position. And again, you might wonder, what if we add it in this position? Well, remember, this is also the meta position. It also forms an M. So something that resembles an M. So this is also the meta position relative to the original functional group. And again, this is also the ortho position. But what determines whether we add this Y compound on the ortho position? Or maybe what determines if we add it on the meta position? Well, what dictates where we add this Y compound? Well, if this X compound, this original X functional group, happened to be an electron donating group, if this X was an electron donating group, it would favor adding the Y compound on the ortho and on the para position. However, if this X compound was an electron withdrawing group, if we had an electron withdrawing group, it would favor adding this Y compound on the meta position. So what's going on? Well, what's an electron donating group and then what's an electron withdrawing group? And why is ortho and para in one category while meta is in a separate category? Well, let's do an example. Let's say we have these two compounds, these two groups. And I'll let you know right now, this is an electron donating group, while this is an electron withdrawing group. So we know electron donating groups favor adding the bromine on the ortho and para position, while electron withdrawing groups, this electron withdrawing group favors adding the bromine on the meta position. So what's going on? Well, first of all, so let's say that Y compound we wanted to add, let's say it was a bromine. If something important to realize is before we just simply add a bromine, we have to make this bromine electrophilic. We need to prime it and make it electrophilic. So we do that by binding it to a leaving group. And the leaving group depends on what kind of compound we want to add, but we bind it to some kind of compound, priming it, making it electrophilic. Now these nucleophilic lone pairs of these nucleophilic pi bonds can nucleophilically attack this bromine electrophile. So these pi electrons attack the bromine, and now they add the bromine and the leaving group falls off. But again, if that was complicating, the point is, if we want to add a bromine, we need to prime it. If we want to add some kind of Y compound, we need to prime it. But let's say it's primed and it's ready, so now we're ready to react. So let's say we want to add this bromine on this ortho position. What would that look like? Well, we know these pi electrons would attack the bromine, forming a bond here. So again, these electrons you could imagine attacking, forming a bond here. And if we did that, we would form this product. When we added on the ortho position, we would create this product. Where again, this carbon lost the electrons in this pi bond. So it lost those electrons, so now we have this carbocation. So that's what would happen if we added in the ortho position. And again, the same thing here. Let's say we want to add this bromine on the ortho position. It's the same idea. We make the bromine electrophilic. Now we can add it on the ortho position, creating this product. But now let's think about it. Which of these two products is more reasonable? Well, again, we know this is an electron donating group, so therefore it donates electron density. We have these lone pairs of electrons that can fall down, forming a resonance structure, donating electron density, stabilizing this positive charge. So this is good. This is good. Adding it on the ortho position of electron donating group is good. This stabilizes that positive charge, so that makes sense. However, this guy is an electron withdrawing group. And the way I like to think about it is this carbon is bonded to these fluorine atoms, which are very electronegative. They're very electronegative, pulling a lot of electron density. As they pull electron density, there's an electron deficiency on this carbon. So this carbon is partially positively charged. So therefore, we have this partially positively charged carbon. So when we add this bromine on the ortho position, we add it on the ortho position, creating this positive charge right next to this carbon, which we already said is partially positively charged. So that's not stable. That's not reasonable to add this bromine on the ortho position, because when we add this bromine on the ortho position of this electron withdrawing group, when we add it on the ortho position, we create a positive charge right next to this electron withdrawing group, and with this positive charge, so these two positive charges nearby each other is not stable. So this is not reasonable, and this will not happen. This will not happen. So that's why electron withdrawing groups don't do ortho and para. They don't like adding it on the ortho position. We'll explain why it doesn't like it in the para position. So that's why it doesn't like adding it on the ortho position. So therefore it's stuck adding it on the meta position. We'll explain that in more detail later. But again, we know this electron donating group doesn't mind adding it in the ortho position. When it adds it in the ortho position, it creates this positive charge right next to this electron donating group, which can stabilize this positive charge. So this is okay. So this electron donating group doesn't mind adding it in the ortho position. And then once we have this, the next step is essentially one of these hydrogens are deprotonate. And as we deprotonate, these electrons fall down, reforming that double bond, creating our final ortho product. So that's adding it in the ortho position. Now let's imagine adding a bromine in the para position. So again, let's say we want to add in the meta position. Let's imagine adding it in the meta position. So again, we take this bromine and we activate it. And we explained how, but again, so now we activate it. So let's now add this bromine in the meta position. So what would that look like? Well, if we add it in the meta position, it's these electrons in this pi bond would attack, forming a bond here. So if we do that, essentially this carbon would lose its pi electrons, and then this one gets, so again, we would form, these electrons would form this bond. And when we do that, we would form this product, where again, this carbon lost its electrons, so now we have a positive charge on this carbon, So that's adding it on the meta position. If we add it on the meta position, we get a positive charge on right here. And again, let's do the same thing here. Let's add the bromine and let's add it in the meta position. If we add it on the meta position, again, we create this product with the positive charge here. So now let's analyze these two positively charged intermediates. Well, this intermediate, it has resonance. These electrons can scooch down. And when they do that, you could draw the resonance structure and see you would have a positive charge here. And then again, you could have another resonance structure creating another positive charge here. So again, I recommend you take out a piece of paper and you see this original compound and you see the resonance structures, and you'll see that you'll have the positive charges on these carbons. And again, the same thing here. You try it out, draw the resonance structures, and if you draw the resonance structures, you would see you would have a positive charge here and you would have a positive charge here. So now, see in both of these situations, this is okay. For example, focusing on this electron withdrawing group, it's okay to add this bromine on the meta position. Because again, we avoid having a positive charge here, which we said this electron withdrawing group, all this electron withdrawing group is thinking is as long as there's not a positive charge added here, that's okay. We can do that. But in the previous video, we saw adding it ortho, we did create a positive charge here, which was not good. However, adding it on the meta position, we avoid that. There's no positive charge here, so that's okay. So this is okay. So it's okay adding it on the meta position. And again, so for this example, if we add it in the meta position, again, there's a positive charge here and the positive charge is here. So again, that's okay. There's nothing good about this, but there's nothing bad about it. So that's okay. So again, now we have these two, and then again, now we can form the final products. And again, the way we do this is, again, we explained, we have hydrogens here, we deprotonate, the electrons fall down, forming the final product. And again, the same thing here. Electron, we steal that hydrogen, these electrons fall down, forming our final product. So that explains why this guy doesn't mind adding it in the meta. When it adds it in the meta, when these electron withdrawing groups add it in the meta position, it's okay. We form these resonance structures with these positive charges that aren't right next to this this carbon positive. So this is okay. So that explains why it doesn't mind adding it in the meta position. So now let's look at the para position. Let's say we want to add this bromine, this bromine on this para position. So again, let's say we have a bromine and let's say we want to add it on this para position. If we add it on the para position, again, these electrons would essentially attack adding it on the para position, and then this guy would get a positive charge. So this is what would happen if we add it on the para position. And the same thing here. Let's say we want a bromine, and let's say we add it on the para position. If we do that, we would form this structure. Now let's analyze these structures, and let's see if they're reasonable. Well, again, we know we have resonance. For example, in this example, we have resonance. And if you drew the resonance structure, you would see you would have a resonance structure with the positive charge here. And again, these electrons falling down, and you would have a positive charge here. But again, remember, this electron donating group can stabilize that positive charge. It can stabilize that positive charge, that explains why this electron donating group likes adding it in the para group position. When it adds it in the para position, it creates this compound which has resonance, which can stabilize that positive charge. It does the resonance, putting that positive charge here, which can be stabilized, and we explained that earlier. So that explains why this electron donating group doesn't mind adding it in the para position, because when it adds it in the para position, it can stabilize this intermediate with resonance. However, this electron withdrawing group, if we add this in the para position, what happens? If we add it in the para position, we would create this structure. So we add it in the para position, we create this structure. And again, this also has resonance. That would have a positive charge here, which we know is not stable. We already explained that this carbon has a partial positive, so we don't want a positive charge here. So therefore, when we add this in the para position, we create this structure which has resonance, which puts a positive charge here, right next to this carbon with this positive charge. So this is not reasonable. This is not reasonable. So that explains why this electron withdrawing group doesn't like adding it in the para. Because when it adds it in the para, it has resonance that has a positive charge here, which is not stable. So again, the point is, these electron donating groups, they don't mind adding it in the ortho position or in the para position. Because when it adds it in the ortho, or when it adds it in the para, it forms these resonance structures that can stabilize that positive charge. It can put that positive charge next to the electron donating group, stabilizing the positive charge. So these electron donating groups don't mind adding it in the ortho and para position because it can stabilize those positive charge intermediates. However, these electron withdrawing groups hate adding the bromine in the ortho and para position. Because, for example, when it adds it in the para position, it has this positive charge that has resonance that puts this positive charge right next to this electron withdrawing group with its positive charge, so that's not stable. So therefore, this electron withdrawing group hates adding it in the ortho and para position because it doesn't like those positive charge intermediates. So therefore, it's kind of stuck adding it in the meta position because that's the only position it can add that doesn't create a very unstable resonance structure. So the way you should think about it is electron donating groups like adding it in ortho and para. When they add it in ortho para, they can stabilize that positive charge resonance intermediate. However, meta position is stuck adding it. This electron withdrawing is stuck adding it in the meta position because the adding it in the ortho and para isn't stable, so it's kind of stuck adding it on the meta position. So now let's do some examples and hopefully this makes sense. So let's say we have this chlorine, and again, let's say this is the chlorine, the compound we want to add. Again, the way we do it is we add it to a leaving group and we make it electrophilic, ready to add. So where would this chlorine add? Would this chlorine add an electron in an ortho position, in para position, or in a meta position? Well, again, the way I like to do this, and then determining if this is electron donating or electron withdrawing, the way I like to do this is I like to just simply, what I do is I just simply imagine adding it in the ortho position. That's always the first step I do, is I just imagine adding it in the ortho position. So if we were to add it in the ortho position, it would look like this. With the chlorine here, adding it in the ortho position with the positive charge here. So that's the first thing I do when solving these problems, is I simply just add it in the ortho position. And I see, does this make sense? Does adding it in the ortho position make sense? Well, if we add it in the ortho position, we create a positive charge here, which is stabilized by resonance. We know we have resonance. We have resonance stabilizing that positive charge, delocalizing that positive charge, and stabilizing that positive charge. So therefore, this would be an ortho-directing group. And we know whenever we have an ortho-directing group, we also have a para-directing group. Because if we add it in the para position, again, it would have a positive charge that has resonance that can have the positive charge next to this group. So we know if we add it in the ortho position, it's stabilized by resonance, so therefore we know this is an ortho-para-directing group. Because remember, ortho and para are in the same category. So that's always the first step I do. So now I know this is an electron donating group. But now, so let's do this example. Let's imagine this example. And let's say this time we want to add another chlorine. Let's say we want to add a chlorine to this group. Would it favor adding it in the ortho para position, or would it favor adding it in the meta position? Well, again, the first step I always do is I just imagine adding it in the ortho position. That's always the first thing I do. I imagine adding it in the ortho position. So if we added it in the ortho position, we would create something that looks like this. So that's always the first thing I do. We see, okay, well, is this ortho or para? Well, I just imagine adding it ortho. So I imagine adding it ortho, and we would create this structure with this positive charge here. And I see, is this reasonable? Is this reasonable? Well, again, we know this nitrogen also has a formal charge of +1. We know you could find the formal charge, so this nitrogen has a formal charge of +1. So we know this is not reasonable. If we add this chlorine on the ortho position, we create this structure, which is not stable. We already have a positive charge on this nitrogen, so we don't want to add another positive charge right next to it. So adding this chlorine on the ortho position is not stable. So therefore, this is not the ortho, and therefore para must not be realistic. So therefore, we're stuck adding it on the meta position. If we